Okay, this is an example problem of how to find the magnetic moment for a non-trivial system. In this case, what we'll be looking at is we want to find the magnetic moment for a spinning charged disk. So a spinning charged disk has some current going in loops, right? And each current loop will have some magnetic moment, and what is the total magnetic moment for the system. In order to find that out, we're actually going to use a fairly simple idea. We're going to add up the magnetic moments for each little part of that, and so mathematically we write that like that. The total magnetic moment is equal to the sum over a bunch of little tiny magnetic moments. Little tiny magnetic moments, of course, would be the magnetic moments from little rings, and so the radius of these rings would be r, and the size of the rings, if we were to look at the size, would be dr. And so we want to know what the magnetic moment for each one of these little rings are. Well, that's actually pretty easy. The magnetic moment for any ring is, any closed loop is the current that flows through that loop. We're going to talk about a differential current this time, so di times the area of that loop. For us, the area is obviously 2 pi r, and so this is not 2 pi r, pi r squared. So little pi r squared di. And so now we need to figure out what the current going through here is. For this, we're just going to use the fact that current, right? Current I is equal to this case we're talking about a flat surface, so this will be some surface current density K times some length. In this case, the length that we're going through, the length that we're going to look at, the length from there to there, which is dr. So dr. Now we have to figure out what K is. Well, K is going to be using the idea, right, the similar idea we have that the current density is the volume charge density times the velocity at each point. We're going to use this exact same analogy that the surface current density is equal to the surface charge density times the velocity at that point. Velocity at that point is just r times omega. So K here is just going to be, or there we go. So magnitude of K is just going to be sigma times r times omega. And so here, as long as we've got our width perpendicular to the motion, which we do, then we can just take the magnitude of K there. So plugging all that back in, up here we're going to get this differential current here. This di is sigma r omega. Plugging that in to our expression for little dm, of course, is going to be sigma omega pi squared, and then we're going to get r squared from there, and r, and we still have this dr, and that's the dr from there. So r cubed dr. So that's what this little moment here. So this, now we're going to write down, if the radius of this full thing is a, we'll write down integral from 0 to a of sigma omega pi squared r cubed dr, which this is a trivial integral. It's an integral of a polynomial, so this is sigma omega pi squared a to the 4th over 4. And that is the magnetic moment due to a spinning charged sphere. I guess I didn't say what sigma was, so I'm not quite done because we haven't figured out what sigma is. Sigma is going to be the total charge divided by the surface area, right? So sigma is equal to the total charge divided by the surface area, which is the total charge divided by pi a squared. So plugging that in, we'll get then, so plugging that in there, we're going to get that the magnetic moment due to a spinning charged sphere is Q omega pi a squared divided by 4. And this, of course, will be in the z hat direction. I missed the direction part of that. This is in hat, which will be z hat. And so that is the magnetic moment for a spinning charged spinning charged disk of total charge Q.